Alrighty, ladies and gentlemen, here we are at 2.2, day 1, higher degree polynomials. We're going to be graphing and finding zeros of degree 3 and higher functions and writing functions based on its zeros. Okay, now one thing before we get rolling too far is the general shapes of graphs of polynomial functions, and right here, taking a look at the even numbered functions, or even powered functions. Alright, so maybe it's not real clear, I don't know how good this is showing up on your screen. But all of these go from negative 3 to 3 in the x, and they go from 0 up to 10 in the y. Alright, so I have a consistent grid to work with here. And, well, anyway, when we have the x squared, notice we have the basic shape. And, it's a parabola, no big surprises, I'm not going to go into that. But then when we get to x to the fourth, no, I'm not going to have you memorize some other pattern for this. But what I do want you to realize is these powers get higher. And it is a little bit of a subtle change between 4 and 6, although it's pretty dramatic, I think, between x to the second and x to the fourth. Notice on x to the fourth that we go a lot more toward vertical on the sides, and we go a lot flatter in the middle. So, kind of in my weird way of looking at things, it gets a little more boxy, I think. Same thing with x to the sixth, it goes up a little bit faster, and it gets a little bit flatter in the middle. So basically, to the extreme case, this thing would be nearly vertical, almost make a right angle, go completely flat, almost make a right angle again, and take off. What they would have in common on all these graphs is the point 1, 1. Because if I take any power of 1, I still get 1 for my y. So basically that's kind of like the point at which these guys really turn and take off. Parabola, not so much. Fourth power starts getting steep, sixth power gets steeper, and basically that's the deal there with the even functions. We have both sides going up, and the higher power it is, the boxier it is as it goes. Okay, now let's take a look at the odd functions, or the odd powered functions, if you will. I've got y equals x to the third, y equals x to the fifth, etc. Okay, and again with the y to the third, we've dealt with this one a lot. We have our nice normal monkey shape. Okay, notice our windows are going to be consistent here from negative 2 to positive 2 in the x, and then from negative 10 to positive 10 in the y, just in case, again, it's unclear on either your screen or the printouts that you have. Alright, so there we are with that. Nice monkey shape for there for x to the fifth. Notice on the side, kind of left and the right edges of this thing, it's a little bit more vertical, and it's not real obvious to tell from these graphs, but it's a little bit flatter in the middle and then more vertical on the edge. So just like the evens, it got boxier, if you will, just kind of boxy and kind of a zigzaggy pattern. And then just as an extreme case here, if I take x to the 13th, alright, I'm nearly vertical on the side, pretty close to horizontal in the middle, and then pretty close to vertical on the end. Again, we have the 1, 1 and negative 1 points common between these guys, but don't worry about that too much. I'm just, want you to know that we've got this nice monkey shape, and the higher the power, the boxier it is. Okay, the kind of follow-up question to this is the x to the first. Does that still fit the pattern? Well, sure enough, I hope you're thinking yes. Because really it's the same basic thing, just a real quick sketch here. If I graph y equals x, well, it goes right through there, and, well, that is the low left, high right pattern, although there's no exponent on there, and the exponent is basically what gives it its wiggle. And so, it's still the same basic idea, but usually we don't think of this as being a part of it because it doesn't have the kind of bend in the middle like the other powers do. But anyway, just so that it still does fit the pattern, so the whole odd exponent being low left, high right thing, it still does hold true to form. Alright, now that brings me to the end behavior, also known as the Lie coefficient test, and it's actually, the book's going to refer to it in a slightly different way. The right hand and left hand behavior of the graph. So there's basically 3 different ways we can mention this stuff that we're about to talk about. But basically all this stuff is just going to depend on the degree and the sign of the Lie coefficient of our polynomial. So basically we want to capitalize on the degree and the sign of that Lie coefficient. Alright, so here's some notation the book uses that I think is some of the worst notation that it uses, but unfortunately we're kind of stuck with it, so here it is. Alright, if we have an even degree and a positive Lie coefficient, so if I have, y equals x to the fourth, y equals x squared, whatever, of course our basic graph is going to look something, like our basic parabola shape. Again, depending on the power, it's going to be boxier or less boxy, depending on the higher or lower power that you have. But this notation here, and again, here's why I hate it so much, is basically you have to look at the x to decide what goes in this box here. So here we go. This says f of x, and this arrow means approaches. approaches. So if you want to write that down, it's probably not a terrible idea. And then as x approaches infinity. So what they're basically asking you is what happens to the y values as x gets really, really, really big in the positive direction and then really, really, really big in the negative direction. And they're looking for whatever that goes in there. And so here's basically what it is. As x gets positive infinity, that means I pick my x values way off to the right. Well, because I'm taking those values to a power, it's going to get a really, really, really big number. So positive numbers to positive powers, or sorry, positive numbers to any exponent is going to get really, really big. So basically this would be read as f of x approaches infinity as x approaches infinity. Although I think you should say the x stuff first. Say as x approaches infinity, comma, f of x approaches infinity. But again, the book is going to do it in this order. The second half of this, we've got negative infinity here for the x, and so if I do negative infinity, and notice how we have even powers here. If I take a negative number to an even power, I'm going to generate a positive result. So as I go to the extreme far left edge of my graph here, taking really, really big numbers to even powers, I'm going to get really, really, really big positive answers out of it. So f of x approaches infinity as x approaches negative infinity. Okay. If we take this the other way, even degree and negative lead coefficient. So again, our basic graph would be something like this, and a negative lead coefficient. Again, whether or not it's a number there or not is irrelevant for purposes of this question. So again, if I throw a negative in front of something like this, it turns itself upside down. So then, as we go to the far extreme right edge of my graph, okay, I take a number, I take it to a power, and then I throw a negative on it. So basically my y value becomes a negative infinity. So f of x approaches negative infinity as x approaches positive infinity. And again, as x approaches the left side of the graph, so I'm talking about the second half here, and I'm taking a negative number, I'm going to take it first to an even power, so it's going to be really, really, really big, but then I'm going to put a negative on it, so on the flip side it becomes very, very small. So boom, this is just a fancy way, this whole slide is a fancy way of saying, hey, if it's positive, both ends are going to go up, and if it's negative, both ends are going to go down. So don't read too much into it, that's all it's saying, it's just doing it with a very, very fancy looking notation. And I'm sure you were observant enough to catch in the last one that everything was about even numbered powers, and so let's talk about the odds. Well, if I have an odd power, again, from what we did on the beginning of this lesson, if I have an odd power, then I've got kind of my barrel of monkeys graph, so it's doing something vaguely like that. Again, boxy, depending on how high of a power you use. But again, as x approaches infinity, so as I plug in my really, really big numbers, I put a positive number to a power. Honestly, even or odd doesn't matter. I'm going to get myself a very, very large number out of it. And here if I put in a negative infinity, well, if I take a negative number to a high power, or even any odd power at all, it doesn't have to be high or low, I'm going to get a negative answer, because an odd number of negatives gives a negative result. And again, it's demonstrated in the graph that the y values get really, really small as we go to the extreme left edge of our graph. So again, all this is saying is if I've got a positive coefficient and an odd power, I'm going to be low left, high right. Okay, and if I have odd degree, negative, okay, again, what we've done from graphing so far, hopefully pretty obvious right here. This guy's going to flip himself upside down, do something like that. And then so translating this fancy notation, as x goes to the right, okay, notice that negative sign in front of everything just flips it upside down and gives us negative infinity. And then as x goes toward the left edge of the graph, okay, we're going to be generating ourselves some very positive big numbers. So f of x approaches infinity as x approaches negative infinity there. Okay, this brings us to real zeros and turning points. Now, real zeros we've done 1,000 times, so we're not going to get into that too much, but that's x values where the function equals 0, and we're going to throw out imaginaries for now. Turning points, this is new, and it's where a graph turns from increasing or decreasing. I mean, we've talked increasing and decreasing, we just never called it turning points before. Well, here we go. Alright, if I've got my function, x squared minus 2x minus 15, the real zeros, of course, you just replace the f of x with a 0. Just because I like to, I'm going to put it on the right hand side. And of course that's something here that's easily factorable, as x plus 3, x minus 5. And then of course that lets us know that our zeros are negative 3 and positive 5. So yawn, no big deal. Okay, now what I'm doing is modeling basically a section of the homework problems here, but now that we found the real zeros are negative 3 and 5, I want to know the multiplicity of the zeros. Well, multiplicity, depending on the math class you had prior to this one, you might know what that means already, but here it is just in case you need it. Okay, the multiplicity is how many times each 0 occurs. Well, if we think about what we're just looking at, I had a single factor that gave me a -3 and a single factor that gave me a 5. So the -3 was simply multiplicity of 1, and then equally so, the 5 was a multiplicity of 1 as well. Alright, so basically there's part of the answer for part B. Alright, now the number of turning points, that's a little bit more confusing, at least for now. Hopefully it gets better soon. But the turning points, again, is the number of times it basically turns from decreasing to increasing or vice versa. And that's all this is here. If we follow our parabola down, well, we hit a low point and then turn around and go back up, so it turned once. And since we know it's a parabola, we know that guy's not going to do anything else somewhere else on the graph. So basically the number of turning points is 1. So second half of the question right there. And this is in our book, and if you want to read on a little bit more, you can. Basically what it equates to, the number of turning points is at most 1 less than the degree of the polynomial. So I had a second power that gave us this, and it turned once. If you think about it, if I have a first power, I just get a line, and there's no turning there, so it's 0, and so hopefully that makes a little bit of sense as you do this. The verify graphically is something that the book is going to ask you to do. Feel free to do that on a calculator, especially when the equations get a little bit messier, but I thought it'd be nice to have the picture there as we talked about turning points, at least for the first time. Alright, let's take a look at one that's got a third power mixed in there. So I've got this, again, finding the real zeros simply means that you got to take this guy, x to the third minus 10x squared plus 25x, set him equal to 0, and then do whatever regular algebraic things you need to do. Okay, in this case I'm going to factor out an x squared minus 10x plus 25 equals 0. Okay, if you're thinking, hey, I just divided the whole thing by x, well, if you did that, you get yourself down to an x to the second, and basically you would lose one of your zeros. So basically it's a good rule, don't ever divide off a variable if you can help it. And quite honestly, I think we always have tricks around that, so we can always help it. So just never divide off an x, or x being part of something else. Usually ends badly for you. Okay, but as we continue, when we factor this guy, x minus 5 equals 0. Okay, I could write this as x minus 5 quantity squared, but I kind of want to bring out the whole idea of x equals 0, 5, and normally you wouldn't have to write 5 the second time, and quite honestly I'm not going to here, because I'm going to kind of deal with that over in part B, the multiplicity. Okay, well, 0, okay, how many times did it show up? Well, it showed up from this one guy here, so 0 has a multiplicity of 1, but if we see this, the 5 showed up kind of twice, even though we only had to write it once. There's going to be some other implications of it showing up later twice, so I want to talk about that now. So we got 0, multiplicity 1, 5, multiplicity 2. Notice that adds up to 3 zeros, and there we are, we had a third power. So that's kind of what we're expecting. So then the number of turning points, again, now I'm going to do this before I have the graph. Well, so the turning points, well, at least for now, I know it's going to be 3, well, actually 2 or less. So 2, I'll throw a little or less on there, although quite honestly in this point it's going to be 2. So I'll just actually squeeze that out of there. Alright, so moving on to part C now, and actually I've already got the graph drawn there for you, and if you print out the PDF then you actually already had it too, but anyway, here we go. Okay, so there's my zeros, 0 and 5, multiplicity of 1 and 2 for those guys, and we knew that there were 2 turning points, or we knew there were 2 or less, and well, sure enough, looking at the graph right now, that right about there I'm turning, and then right about there I'm turning. Okay, this point has kind of a double duty right now because it's a turning point and it's also the zeros. And actually that's no coincidence at all based on the multiplicities. Basically what's going to happen is anytime I have a multiplicity of 1 like this 0 right here, notice that the graph just passes cleanly through the 0 from the negative to positive side, or it could be vice versa, but in this case it's from negative to positive. Okay, and then we go through a turning point, yada yada yada. And if I have multiplicity 2 at a 0, okay, notice what happens is the graph comes down, hits that point, and then takes off on the same side of the x-axis. So basically what's going on there is a second power multiple of a 0 gives me kind of a second power look to my graph right there. So I have kind of a parabola-esque piece of the graph, and it's because I have a multiplicity of 2 on that 0. Alright, so that's something to kind of keep in mind as we go through this stuff, that anytime you have a multiplicity of 2, the way it's going to behave as it hits the x-axis, versus if it has a multiplicity of 1, that's going to be a nice tool for helping us graph these things by hand in the future. Yes, I said by hand. Alright, so now taking a look at another one. I really just have this one for one purpose. As I go about finding the zeros here, whole thing, x to the 5th plus 6x to the 4th, etc. And saying m equal to 0, I have a GCF this time of x squared, so I'm going to pull that guy out first, leaving me with x to the 3rd, etc. 6x squared plus 12x plus 72. Okay, and then from there, hopefully you'll look at this and think, ooh, that's 4 terms. That's something I can do by factoring by grouping. So that's exactly what I'm going to do here. Okay, be careful with this, but I'm going to pull out an x squared inside this parenthesis, leave me an x plus 6, and then pull out a 12 from the second half, again leaving me with an x plus 6, a second parenthesis closes, equals 0. Okay, and then again, basically, the x squared is just hanging out there having a good time. Okay, I pull out the x plus 6 as the first parenthesis, and then the x squared plus 12 is left. I don't technically need that second set of parentheses around the whole thing at this point because, you know, I've indicated a multiplication there and it's still being indicated, so I can do without another grand set around the whole thing. But there we go. Okay, and then my zeros, now notice this is x times x, so if I think of that as x equals 0, I can think of it as x equals 0 twice basically. So as I get this 0, I do know that he's going to be a multiplicity of 2. This guy gives me a negative 6, and then over here, okay, notice I've got x squared plus 12 equals 0, so just off to the side real quick, if I try solving this guy, I'm going to be dealing with x squared equals negative 12, and I'm square rooting a negative, and all of a sudden it gives me i's. And i's we're going to disallow again, like I said, so I don't need that comma, but all I need is a box around those two numbers. Again, now I move over to the multiplicity, and I kind of already said it, but 0 is going to give me a multiplicity of 2 because there were 2 of them, and then the negative 6 we have is only a multiplicity of 1. Okay, now you might be thinking, hey, we're supposed to have 5. Well, we did have 5. 2 of them were imaginary, and so we had to throw them out. So I have 3 reals and 2 imaginaries that we're not going to consider, at least for this type of problem. And again, just taking a brief look at this, once we've got our zeros and our multiplicities figured out, oh, I forgot to say it in the last one, but 2 turning points, and I don't think we actually could have said that until we graphed it, but on the last one we could have said, no, 4 or less. But as it plays out, this guy only had 2. So I got a turning point up here, another turning point down there. Again, notice that because I had the multiple 0, that I do have a 0 that actually also serves double duty as a turning point. And then again, I had this negative 6 with multiplicity 1, and the graph just passes clean through. So again, multiplicity 1 goes straight through, turns around, and then multiplicity of 2 at the 0 means it like bounces off the x-axis, if you will. Alright, another part of this assignment is being able to write a polynomial function based on its zeros. So basically what I'm giving you here is 3 zeros for a function. Alright, now there's more than one way to do this, but and more than one correct answer actually is. But here we go. So I want my function. Well, if I got 3, just think of the factor that would have given you a 3. Well, it'd be an x minus 3. So basically, just duplicate that in there. Again, the x minus 5 would come from an x plus 5, and then the positive 5 would come from an x minus 5. Okay, and if that was weird, well, just think of what 3 solutions you'd get out of this if it was set equal to 0 right now. Well, you'd get those 3. Okay, and then I'm sure you don't want to watch me do FOIL for the next hour and a half, so I will want you to simplify this if you can, but if you can just trust me on this one, this works out to be x to the 3rd minus 3x squared minus 25x plus 75, if we do all that FOIL. So that's what my answer should be after a little bit of FOIL on that original setup. Alright, now this one's a little more interesting. Alright, I've got 3 zeros, just like the last one, although they have much messier looking zeros. Okay, this I could have written as 2 plus or minus root 3, but I was trying to stress a point about this, and here it is. Okay, well the 0, of course, would come from just an x by itself. I mean, I could write x minus 0 or something like that, but I think that's kind of silly. Okay, then from there, and I'm going to purposely use a bracket here. Okay, I've got x minus, you know, the last problem was always x minus whatever the 0 was. Even with the minus 5, it's really x minus negative 5 is where the x plus 5 came from. Okay, but here I have to do x minus that 2 minus root 3 thing. Okay, Likewise, I have to do x minus the other 0, which is, by no coincidence whatsoever, 2 plus root 3. Okay, of course, no surprise, because when you do the quadratic formula completing the square and give that kind of an answer, it's always in a plus or minus sort of format, so hopefully that's not too much of a shock. Alright, at this point though, this is about to get a little bit messy. The x is okay. I'm going to downgrade the bracket to a parenthesis now, because I'm going to distribute this negative sign through here to get x minus 2 plus root 3. And do the same thing here. You get x minus 2 minus root 3. Okay, so basically what I'm looking at now, I don't want to distribute this x yet, I'm going to save that to the end. But what I'm looking for is 3 terms here and 3 terms here, so I'm about to do sort of a mega FOIL. And I'm about to get 9 terms. Okay, now the good news is some of those terms will cancel themselves out, but certainly not all of them. So brace yourselves, here it goes. X times x is x squared. X times negative 2 is a negative 2x. X times negative 3 is a negative x root 3. I like to write my roots last. And then we've got negative 2 times x. I got a negative 2x. That'll combine nicely with that guy there. Negative 2 times negative 2 is a positive 4. And then negative 2 times negative 3 is a positive 2 root 3. Alright, 2/3 of the way done. Root 3 times x is a positive x root 3. Root 3 times negative 2 is a negative 2 root 3. And then finally the root 3 times negative root 3 is going to be a positive, well technically negative root 9, so it's a negative 3. Sorry about that pause slipping out of my mouth there. Alright, so there's that. Okay, I'm going to switch over to red real quick. And notice here we've got a negative x root 3 and a positive x root 3, so those guys cancel. Likewise, I've got a negative 2 root 3 and a positive 2 root 3, so those guys are gone. Okay, so now just going back to what we have left. I've got f of x and I've got x. I've got an x squared that doesn't have any like terms with anybody else. I've got a negative 2x and another negative 2x, so that gives me a minus 4x. And then looking through, I've got 2 other terms. I've got a positive 4 and a negative 3, so that gives me a positive 1. Alright, and then from there, all I have to do is distribute my nice little x that's all by himself there. And then I've got x to the third minus 4x squared plus x. So then there's my polynomial that had those as answers. I did mention there's more than one right answer, because imagine for a second if you multiplied through by a 2. If you did, you'd get the same zeros, because basically you just have a 2x out in front, which would still give you the 0. You just have a constant out there, well, coefficient if you will, which would make our graph stretched out vertically, but it wouldn't change what the zeros were. So I like trying to keep my coefficient low as possible, so I don't multiply through by any other number, because quite honestly I think that's just plain old silly. Alright, and as per usual, what I'm trying to do is give you an assignment ahead, in case you want to jump on in advance, but there it is. Good luck, see you guys in class.